Welcome back to my channel tutorial. After previously discussing the basics of Supermap, now we will discuss the projection and coordinate system. Before we start this tutorial, I'm going to explain the theory of projection and coordinate systems on supermaps. First, let's talk about the projection system that is often used in Supermap. The first is the Mercator projection. The Mercator projection is a cylindrical map projection presented by the Flemish geographer and cartographer Gerardus Mercator in 1569. It became the standard map projection for nautical purposes because of its ability to represent lines of constant course, known as rhumb lines or loxodromes, as straight segments that conserve the angles with the meridians. Although the linear scale is equal in all directions around any point, thus preserving the angles and the shapes of small objects, which makes the projection conformal. The Mercator projection distorts the size of objects as the latitude increases from the equator to the poles, where the scale becomes infinite. The second is the Gauss-Kruger projection. The Gauss-Kruger projection is conformal with a constant scale on the central meridian. The ellipsoidal form of the transverse Mercator projection was developed by Carl Friedrich Gauss in 1825 and further analyzed by Johann Heinrich Louis Kruger in 1912. The features of the projection are, near the central meridian the projection has low distortion and the shapes of Africa, Western Europe, the British Isles, Greenland, and Antarctica compare favorably with a globe. The meridians at 90° east and west of the chosen central meridian project to horizontal lines through the poles. The more distant hemisphere is projected above the North Pole and below the South Pole. The equator bisects Africa, crosses South America and then continues on to the complete outer boundary of the projection. The top and bottom edges and the right and left edges must be identified, i.e. they represent the same lines on the globe. Distortion increases towards the right and left boundaries of the projection, but it does not increase to infinity. Note the Galapagos Islands, where the 90° west meridian meets the equator at bottom left. The Gauss-Kruger projection is now the most widely used projection in accurate large-scale mapping. The third projection is the Universal Transverse Mercator, or UTM. The Universal Transverse Mercator, UTM, conformal projection instead divides the Earth into 60 zones, each being a 6-degree band of longitude, and uses a secant transverse Mercator projection in each zone. The fourth projection is Lambert's projection. A Lambert conformal conic projection, LCC, is a conic map projection used for aeronautical charts, portions of the state plane coordinate system, and many national and regional mapping systems. It is one of 7 projections introduced by Johann Heinrich Lambert in his 1772 publication Amerkungen und Zusatz zur Entwerfung der Land- und Himmelscharten. The distribution of the transformation of the Lambert projection is: the angle doesn't change, which means that the shape of infinitely small area is similar. The distortions in the same parallel are the same. There are not any distortions at the two standard parallels. At the same meridian, distortion length ratio is less than 1 between the two standard parallels. Distortion length ratio is greater than 1 at the two standard parallels outside. The length of latitude and longitude lines between two parallels is the same. In Supermap, there are 3 types of coordinate systems: planar coordinate systems, geographic coordinate systems, and projected coordinate systems. Planar coordinate system is generally used as the coordinate reference of data that is a relative to geographical location, and is also the default coordinate reference of new data. For example, CAD files, scanned picture of a paper map, a sketch map that is a relative to geographical location. Planar coordinate system is a two-dimensional system. The coordinate of its origin is 0, 0, and the coordinate of other points can be measured by the vertical distance from the point to x and y axis. The second is the geographic coordinate system. It uses longitude and latitude to denote any location on Earth's spheroid. In geographic coordinate system, the definitions of datum, prime meridian, and units of angle are usually included. WGS 84, Beijing 1954, Clark 1866 are commonly used geographic coordinate system. Many data, such as KML data of Google Earth and GPS data, employ WGS 84 as coordinate reference. In China, the coordinates of control points from Geodetic Survey use Xi'an 80 or Beijing 1954 as coordinate system. Below is a map of the world that uses WGS 84 as coordinate system. The third is the projected coordinate system. It uses various projection types to make any location on Earth's spheroid projected onto a plane. It uses two-dimensional planar coordinate system to denote the locations of point, line, and region features. In projected coordinate system, the definitions of geographic coordinate system, map projection, projection parameters, and units of distance are usually included. Gauss-Kruger, Albers, Lambert, and Robinson are commonly used projected coordinate system. Generally, projected geographic data can be used in measurement, spatial analysis, and mapping, etc. For example, the basic scale topography map of China uses Lambert projection on the scale 1:1 million, and most of others use Gauss-Kruger projection with 3-degree zone or 6-degree zone. In urban planning, large-scale maps, such as road construction map and architecture design map, with the scale of 1:500 or 1:1000, often use planar coordinate system. Now we go back to Supermap software. Create a new data source and name it however you want. Don't forget to save your workspace. In the newly created data source, as in the previous video, by default the selected coordinate system is China's global coordinates. You can convert it to the WGS 84 global coordinate. Create a dataset. For example, I will create a point dataset with the WGS 84 coordinate system. To see the coordinate system contained in the Supermap, you can go to the Start tab, Data Processing, then Projection Settings. Here is a coordinate system template that you can use. Here there is also a menu to make a new datum according to your needs. For example, I will make a new datum with the ellipsoid I use is Bessel 1841. Now let's try importing data from another format. For example, I have GIS data in shapefile format. I will call the data that already has a coordinate system. After we import all the shapefiles, we will see the coordinate system that already exists in the shapefile. We can see that the shapefile that I imported has a geographical coordinate system using datum WGS84. This file does not have a projection system yet. Now we'll try to set the projection system to the shapefile we imported. You can set the projection system by pressing the Projection Transformation button. Name the shapefile for the output. I know that this area is located in Zone 49 UTM, so I will choose UTM with Zone 49 south of the equator. If we check again, you will be able to see the difference in the coordinate system before and after I changed it. If we create a new map with datasets that we have changed and those that have not been changed, we will be able to see the difference. If you are observant, the center map of the map that has been projected in Zone UTM 49 is different from the one that has not. Now let's look at the other datasets. It can be seen that the other datasets do not have a coordinate system. However, we know that the dataset uses the WGS84 datum geographical coordinate system. To change or set the coordinate system from another dataset that already has a coordinate system, you can press the From Other Data button. In the From Dataset section, select a dataset that already has system coordinates. Remember that the original dataset is a geographical coordinate system, so you should not copy from the dataset that has been projected to Zone 49 UTM. This will cause errors. As an example, I will show you if we copy the coordinate system incorrectly. I copied the data of the coordinate system, which should be the geographical coordinate system, but I will copy the data that has been projected to Zone 49 UTM. This will cause mispositioning of the datasets. Supposedly, if you want to change to a 49 UTM projection, you will have to go through the projection transformation process as in the previous step. If we see if the dataset has the correct coordinate system, the data will be displayed without any errors. However, if there is incorrect data, then the data will not be superimposed on each other. We see once again, the wrong data if it is overlaid with other data will not be merged. We can change it back by pressing the Reset Coordinate System button and select Geographical. Then we will try to reshow it together. You can export the coordinate system and save it as an XML file. Then you can import the XML file into a dataset that doesn't have a coordinate system yet. For example, I'm going to change my dataset for the first time at the beginning of the video, which is dataset point 1. This is okay to do, because unlike the previous case, the point 1 dataset does not have spatial data at all. Then you can add spatial data at point 1. Thus, data point 1 already has an object point entity that is projected in zone 49 UTM with a WGS84 datum. Finally, I will show you what if you are going to transform the coordinates with a different datum. Suppose I have a translational shift parameter from the WGS84 datum to the Basel. Return to the Projection Settings menu, then on the Settings button enter the Shift Translation parameter. Select the Basel datum I made earlier at the beginning of the video. Then click OK. Display both data and you will see the point shift between one datum and another. I think that's enough of my video about the coordinate system. I hope you really understand this, because it is very important so that there is no misposition. See you in my next video. Don't forget to like and share this video.